Hello friends, welcome to this fourth video on analytic function. This video will deal with Laplace equation and harmonic function. First we will see what is meant by an Laplacian operator. An operator of the format dou square by dou x square plus dou square by dou y square is called as an Laplace operator and it is denoted by del square. This operator can take in an input which is a function and can generate an output for that, which means whatever be the input function, it differentiates it partially 2 times with respect to x and 2 times with respect to y and adds the quantity. So this is the role of your Laplace operator. Now, if you give an input phi of x comma y to the Laplace operator, then what will happen? This Laplace operator will take the input for your phi and generate this quantity which is equal to dou square phi by dou x square plus dou square phi by dou y square. And now in case if this quantity is being equated to 0, that is if I have my del square phi to be equal to 0, what do you call this equation as? This equation is referred by the name Laplace equation. Okay, so what is meant by a Laplace equation? A Laplace equation is one that is given by del square phi equal to 0. That is your del square phi equal to 0 is. So a Laplace equation is one that is given by del square phi equal to 0. Now this function phi which is satisfying the Laplace equation is called by the name harmonic function. Okay, so this function phi which is going to satisfy this Laplace equation is referred by the name harmonic function. Okay, the operator is called as a Laplacian operator. When you input a function phi for it and compute the data, you call it to be a Laplacian value. If this can be equated to 0, you call it as a Laplace equation. And a function that satisfies the Laplace equation, that is on substitution, if the value becomes equal to 0, then you call that function to be an harmonic function. So now we will move on to the next slide, which will tell us about the properties of the analytic function. The real and the imaginary part of an analytic function w is equal to u plus iv satisfies the Laplace equation in 2 dimensions. That is, what is the real part over here? The real part of the analytic function is going to be u, which says u satisfies the Laplace equation. So over here, in place of phi, I am going to substitute u. So what will be my Laplace equation? Del square u will now become equal to 0. And again the imaginary part. What is the imaginary part over here? V is my imaginary part. This V also satisfies the Laplace equation. So we have del square V to be equal to 0. This is my first property. The second property says if W equal to U of x comma Y plus IV of x comma Y is an analytic function, the curves of the family U of x comma Y equal to A and the curves of the family V of x comma Y equal to B cut each other orthogonally. What do you mean by orthogonally? The curves are going to be perpendicular to one another. Can you say what is going to be the conditions for orthogonality? You're right. The condition for orthogonality is that the product of the slopes m1, m2 must be equal to -1. So, if the slope of the curve u equal to a and the slope of the curve b equal to b are going to cut each other, then what happens? They cut each other orthogonally. So the angle between each one of them is going to be 90 degrees. So these are going to be the two properties of analytic function. Now we are going to try to see how we can use this property to solve our problems or verify these properties of analytic function. So the first problem will be if I have. Now we will try applying this property to a problem. If u is x comma y is e power x x cos y minus y sin y, we will show that this u is going to be harmonic in nature. What do you mean by harmonic? Harmonic means it has to satisfy the Laplace equation, which this u which we have taken. So del square u must be proved to be equal to 0. So on expansion, what does this mean to us? Dou square u by dou x square plus dou square u by dou y square must be equal to 0. So I have a u from which I can find the first derivative dou u by dou x and dou u by dou y. Next, from this I can go to find the second order derivative dou square u by dou x square partially with respect to x and dou square u by dou y square partially with respect to y. And on adding, this must be giving me the answer as 0. If it gives us 0, then I can show that u is going to be harmonic. So we will first expand the function u of x comma y as e power x cos y minus e power x y sin y. So I am going to do partial differentiation first with respect to x. So what is going to be over here with respect to x is I have two quantities x e power x. So both of them are of different nature. Hence I will have to use product rule. The differentiation of uv is given by u into v dash plus v into u dash. So this is going to be my product rule which we are going to apply it over here. With respect to x, cos y is going to be a constant and hence we can write this as keep e power x as such, differentiation of x is 1 plus keep your x as such, e power x on differentiation is e power x minus in the second term y sin y is going to be a constant and e power x on differentiation with respect to e power x gives you e power x. So my first derivative is now over. So let me expand it as e power x cos y plus x e power x cos y minus y sin y into e power x. This is my dou u by dou x. Let me go for the second derivative, dou square u divided by dou x square. So I am differentiating again partially with respect to x, but which quantity? Dou u by dou x. So with respect to x, cos y is going to be a constant. E power x on differentiation is e power x plus the second term cos y is going to be a constant. X e power x on differentiation is x, you keep it as such, e power x on differentiation is e power x plus e power x you keep it as a constant, x on differentiation is going to be equal to 1 minus the next term y sin y is going to be a constant, e power x on differentiation is e power x. So now this e power x and this e power x into cos y makes it as 2 e power x cos y and the next term will be x e power x cos y minus y sin y into e power x. So I have now completed my dou square u divided by dou x square. My next part is to go and compute dou square u by dou y square. So how to go about it? You will have to again start with your u. So what is going to be your u? Your u is going to be equal to copy paste it from over here, e power x into x cos y minus e power x into y sin y. So I will differentiate your u with respect to y partially now. With respect to y, e power x into x is a constant. Cos y on differentiation gives you minus sin y. So take an idea, differentiation of sin y is going to be cos y and differentiation of cos y is going to be minus sin y. So the first term must be now differentiated. When it comes to the second term, e power x is a constant. You have two terms which is involving y. So again I will have to apply uv rule, which is u into v dash plus v into u dash. So what will happen? Keep your y as such. Sin y on differentiation is going to be cos y and you keep your sin y as such. Y on differentiation gives you 1. So now this completes my first derivative, namely minus x e power x sin y minus e power x y cos y minus e power x sin y. So I am having my first derivative. I will go for my second derivative, dou square u divided by dou y square. So when I differentiate it one more time with respect to y, minus x e power x is a constant. Sin y on differentiation gives me cos y. The next term minus e power x. Two terms are there. So you go for the product rule. Keep y as such. Cos y on differentiation gives you minus sin y. Plus cos y you keep it as such. Y on differentiation is going to be 1. Minus e power x into the sin y on differentiation gives you cos y. Now let me simplify the data. Minus x e power x cos y minus into minus will give me plus e power x y sin y minus e power x cos y, and this is going to be minus e power x cos y. So I have minus x e power x cos y plus e power x y sin y. These two quantities on clubbing gives you minus 2 e power x cos y. Now both our derivatives are ready. So we are ready to add our first and the second term. So minus x e power x cos y. Go plus e power x cos y. So both of them are of opposite sign. The next term is 2 e power x cos y. Over here I have minus 2 e power x cos y. So they will cancel off each other. The third term is e power x y sin y. Here I have e power x y sin y but with the negative sign. So what is the idea? When I had this dou square u with dou x square with this dou square u by dou y square, what will be getting? We will be getting the two quantities on adding dou square u by dou x square plus dou square u by dou y square to be equal to 0. So what has happened over here? I have proved that the Laplace equation is true for my function u. So u satisfies the Laplace equation. So u satisfies dou square u by dou x square plus dou square u by dou y square equal to 0. So the Laplace equation is true for u. Hence, what do you call u as? U is called as an harmonic function. You call it as harmonic function. Okay. So now we will see how to apply the second property to a problem. So that is going to be our next challenge. The second property is to show that the verify the curves of u equal to a and b equal to b cut orthogonally when w is equal to u plus iv, which is equal to z cube. Okay, so I have w equal to z cube to be my function. W is equal to z cube is my function. So this is going to be x plus w is going to be u plus iv. So I have x plus iy the whole cube to be equal to your u plus iv. So I need to use my a plus b the whole cube formula for my expansion. So what is my a plus b the whole cube? X cube plus 3x square y plus 3xy square plus y cube. So I am going to expand it using this format. So it gives me a in place of, this has to be x plus y. Okay, so you can rewrite it as x plus y the whole cube. Okay, so now in place of x plus y, I have x plus iy. So this is x cube plus 3x square and y. In place of y, I have iy plus 3xy square. So it is iy the whole square plus the last term is iy the whole cube. So this is going to be my u plus iv. So my idea is to get what is going to be my curve u is equal to a and v equal to b. So I have to subtract my real part separately and imaginary part separately. On expansion, this gives me plus, this is going to be I 3x square y. I square makes it as minus 1. So 3x. So this will become y square. And this now makes it as I cube. I cube is going to be I square times of I. I square is going to be minus 1 times of I. So this makes it as minus I into y cube. So this is my u plus iv. Collect all your real parts separately. What is going to be the real part? X cube is the real part and 3x square y square is going to be your real part. So x cube minus 3xy square is going to be your real part, and collect all your imaginary parts separately. What is going to be your imaginary part? 3x square y and minus y cube is your imaginary part. So plus I times of 3x square y minus y cube. So this is going to be your u plus iv. How can you compare two complex numbers? The real parts have to be equal independently and imaginary part has to be equated independently. So from over here, I have u is equal to x cube minus 3xy square and I have v to be equal to 3x square y minus y cube. So I have to show that u is equal to a. So this x cube minus 3xy square is equal to a curve, and b equal to b, 3x square y minus y cube is equal to b curve has to cut orthogonally. So what is going to be the condition of orthogonality? We have already seen that the condition for orthogonality is, so the condition for orthogonality is m1 m2 equal to minus 1. So what is going to be my first curve? My first curve u is equal to a is going to be given by, what is going to be my x cube minus 3xy square, x cube minus 3xy square equal to a. Let me go for the derivative to find my m1. That is going to be my dy by dx. So differentiating this equation with respect to x, then what we have is x cube on differentiation is 3x square minus 3 into, now x, y, both of them are variable. Keep your x as such. Y square on differentiation is 2y dy by dx, plus keep your y square as such. X on differentiation with respect to x gives you 1. And this equal to a will now become equal to 0, a constant on differentiation. 3 over here can be cancelled off on both sides. So this gives you x square is equal to 2xy dy by dx plus y square, because I take this minus sign to the opposite side. So just bring this y square to the opposite side. So it is x square minus y square, and cross multiply it with this constant or coefficient over here to xy. So that gives me my first slope dy by dx to be equal to x square minus y square by 2xy. Now my idea is to go for the second slope. What is my second slope? That is given by v equal to b. So what is going to be my v equal to b? So copy paste your v equation. What is your v equal to be? 3x square y minus y cube. 3x square y minus y cube equal to b. Now again I need my slope y2, which is my dy by dx. So differentiate it again. So what happens over here? Both of them are variables. Keep x square as such, y on differentiation is dy by dx, plus keep your y as such, x square on differentiation is 2x, minus y cube on differentiation is 3y square into dy by dx, and this b on differentiation becomes 0. This 3 can be cancelled off by taking it to the opposite side. X square dy by dx plus 2xy will be equal to, take this quantity to the opposite side. So you have minus will become plus y square dy by dx. You can also take this quantity over here to the opposite side and club all your dy by dx together. So in which case dy by dx will be equal to y square. So this will be equal to y square, when I take this to the opposite side, will become minus x square. This will be equal to 2xy, and hence dy by dx will be equal to 2xy divided by y square minus x square. This is my m2. Now what I need to show, the next page I need to show that m1, m2 equal to minus 1. We will copy paste our m1 from over here. What is my m1? My m1 is going to be equal to x square minus y square into 2xy. So it is x square minus y square divided by 2xy. What is going to be my m2? Copy paste it from over here. My m2 is going to be equal to 2xy divided by y square minus x square. So this is going to be 2xy divided by y square minus x square. So now take this minus sign opposite outside from over here. So I will have x square minus y square, 2xy, and over here it is 2xy, and you will have minus sign of x square minus y square. So this can be cross multiplied and then cancelled off, leaving you with minus 1. Hence I have shown that m1, m2 equal to minus 1. Hence the curves u is equal to a and v equal to b cut orthogonally. So we have proved that two properties of analytic function, namely in the real and the imaginary part satisfies the Laplace equation, and hence they are called to be harmonic in nature, and the curves u equal to a and v equal to b cut orthogonally if they are going to be the real and imaginary part of an analytic function. Thank you.